In 2.5, we're going to look at doing what's known as implicit differentiation. And the difference between this and the derivatives that we've done in the other sections is how our equation is structured. On all the other equations that we've done, we've had y equals or f of x equals or s of t equals, and we would have one variable on the other side. So if we're able to solve an equation for a single variable and we have one variable on one side, the other variable by itself, then this is said to be able to be solved explicitly. But if we have an equation that is not solved where we have just one variable on one side and just one variable on the other side, then that's referred to as an implicit equation. So how do we handle when we have x's and y's mixed together on the same side, could be multiplied or divided together? How do we handle that? Now, you might look at this one and say, well, we could get y by itself, and that is true. We could isolate y in this equation. But there are going to be many equations that we are not able to isolate y or any other variable. So we need to be able to handle taking the derivative even if our y is not isolated. So most of the time, we're still going to be looking for dy over dx because we're going to have some function or some equation, and we want to know the slope at various points. Also, let's make note that all of the things that we've done so far have been functions. But if we have something such as x squared plus y squared equals 9, that's something that we could get a tangent line to, but it's not a function. That's actually a circle that's centered at the origin with a radius of 3. Circles have tangent lines, so we need to know a dy over dx for that equation. But how are we going to handle that if it's not just a function, where we have a y by itself, our independent variable on the other side? So let's start off with this example. And since x is our independent variable, we're going to begin by taking the derivative with respect to x. Just like we have on all the other equations that had y equals something with x's or f of x equals something with x's, we're going to differentiate with respect to x. So we have three terms, so we're going to differentiate the first term with respect to x, and we're going to differentiate the next term with respect to x, and we're going to differentiate the 10 with respect to x. Notice I've not applied a derivative yet. I've just expressed how the derivative will be taken. It will be taken by differentiating each term separately. In this first term, we can put the 3 in the front, and then we can take the derivative of the variable part. Same thing on the next term, put the 7 in front and take the derivative of y. And then on the right side, take the derivative of 10. So what do we get here? Bring the 3 down. The derivative of x squared is 2x. 2x. Here we have a 7. But here, what is the derivative of y? Well, when we had equations like y equals something, when we took the derivative, we got y prime or dy over dx on the left side, and then we just took a regular derivative of the x squared. So when we take the derivative of y with respect to x, that's known as dy over dx. On the right side, the derivative of 10 is 0. Another way we could think of this is that the derivative of y, or a variable by itself to the first power, is 1. If these variables match, then we just simply take the derivative. If these variables don't match, then we have to pick up a dy over dx, or a derivative of that variable with respect to that variable. But for right now, just let's think about it as the derivative of y with respect to x is dy over dx. So that gives us 6x plus 7 dy over dx equals 0. We can subtract 6x from both sides, so get 7 dy over dx equals negative 6x, and then divide both sides by 7. So dy over dx equals negative 6 over 7x, or negative 6x over 7. So we're still just basically taking a derivative. Now let's take a look at this one. So if we're going to find dy over dx, we need to take the derivative with respect to x. So we're going to take the derivative of the first term minus the derivative of the next term equals the derivative of the right. So the derivative of x with respect to x, that's just 1. The derivative of y with respect to x, we said is dy dx, or 1 dy dx. Now we need to take the derivative of this. Notice we have a product of two variables. So if we have a product of two variables, we have to use the product rule. So let's call u x to the 8th. So u prime, the derivative of this with respect to x, is 8x to the 7th. Now v is y to the 9th, so we need to take the derivative of that with respect to x. So this is just the chain rule. In the last video, I did not specifically mention the general power rule, but if we're taking the derivative with respect to x, and this is a different variable, then if we use the chain rule or the general power rule, it says bring the exponent down, do that to the 1 less power, our input stays on the inside, times the derivative of the inside. Notice this is not just x this time, this is y. So when we bring the 9 down and do that to the 1 less power, we also have to multiply that times the derivative of the inside part. That's a different letter, so we could think of that as a whole function. So v prime is 9y to the 8th times dy over dx. So essentially, when we take a derivative and our variable is different than what we're taking the derivative with respect to, we still take the derivative, but we have to pick up a dy over dx. So what is the product rule? It's u prime times v plus u times v prime. All right. So notice we have dy over dx in two different places. So in order to solve this for dy over dx, we want to isolate those two terms on one side, put everything else on the other side. So subtract this from both sides, so that those cancel. When we do that, both terms on the left side are going to have a dy over dx. So since these have a common factor, we can factor out their common factor. If we take that out of the first term, that's 9x to the 8th y to the 8th. If we take it out of the second term, we're left with the coefficient 1. And then to get dy over dx by itself, divide both sides by that parenthesis. Those cancel, so dy over dx is 1 minus 8x to the 7th y to the 9th over 9x to the 8th y to the 8th minus 1. So that's our derivative here using implicit differentiation. So let's do another. So let's take the derivative with respect to x so that hopefully we can get dy over dx at the end. So we have a product. We have something with a variable times something with a variable. So let's call this u and that v. So if u is 6 cosine of 9x and v is sine of 8y, we need to find u prime and v prime. So u prime, 6 is a coefficient, so leave it alone. Then this is the chain rule. The chain rule. So the outside function is cosine, so the derivative of cosine is minus sine times the derivative of the inside function. The inside function is 9x, and that derivative is 9. So a positive times a negative times a positive is negative. 6 times 9 is 54 times sine of 9x. So that's u prime. So now we need v prime. So this is the chain rule again. So the outside function is sine. So to take the derivative of sine, that's cosine, times the derivative of what's on the inside. And this time, instead of actually taking that derivative, I want to write it down. So we have the cosine of 8y times, when we're taking the derivative of this, 8 is a coefficient, so leave it alone, and take the derivative of y. And since our variables don't match, since this is a y and this is an x, the derivative of y with respect to x, we call either y prime or dy dx. If it was just the derivative of x, that would be 1. But since this variable and that variable are different variables, the derivative of y is dy dx. Just like if we had this equation, if we took the derivative of this equation, the derivative of x is 1, the derivative of a constant is 0, but the left side we don't say, well, the derivative of y is 1. We call that either y prime or dy dx, the change in y over the change in x. So that's what we have to do here. So since we have our components, then it's u prime times v plus u times v prime. Let's put the cosine, the 8 dy dx first, and then the cosine 8y. And then the derivative of the right side is just 0. So u prime v plus u v prime. All right, so we basically have two terms. We have all of this plus all of that. So if we want to get the dy over dx term, or dy over dx by itself, if it has a dy over dx on it, keep it on the left. Everything else move to the right. So we're going to add this to both sides. So add 54 sine 9x sine 8y to both sides. Those cancel. That's going to leave us, let's see, 6 times 8, so 48. 9x cosine 8y dy dx. That's on the left. And then when we move this to the other side, it's going to be positive 54 sine 9x sine 8y. Get dy over dx by itself. So the opposite of multiplying is to divide. So divide by 48 by this cosine, by cosine 8y. So those and those cancel. So we get dy over dx. On the right side, we have some reducing we could do. 6 goes into 54 9 times. 6 goes into 48 8 times. Also, notice we're doing sine divided by cosine. As long as those variables, as long as the inputs are the same, sine over cosine is tangent. So we could call that tangent 9x. Same thing here. Sine 8y over cosine 8y, that's tangent of 8y. And then out front we had a 9 over 8. So that's dy over dx. Let's do another one, and then they ask us to find the slope at a specific point. So if we differentiate this with respect to x, we have to use the chain rule. We have an outside function and an inside function. So the derivative of tangent is secant squared. And then we have to multiply that times the derivative of the inside function. On the right side, the derivative of 4x is 4. So we need to finish our derivative by taking the derivative of the inside part. So secant squared of 4x plus y equals, times the derivative of 4x is 4. The derivative of y is dy over dx, and that equals 4. We want to get dy over dx by itself, so we could do this several ways. I think what I will do is I will get this parentheses to the other side, so divide both sides by secant squared. So that leaves us 4 plus dy over dx equals 4 over secant squared. We could leave that secant squared on bottom, but remember that 1 over secant is cosine. Cosine is 1 over secant. So if we have 1 over secant squared, that's equivalent to cosine squared, leaving our input. And then to get dy over dx by itself, subtract 4 from both sides. So those cancel, so we get dy over dx. On the right side, we have a common factor of 4, so we can take a 4 out. And we can call that cosine squared 4x plus y minus 1. Now, in their answer, whether I like it or not, they express their answer differently. They actually express their answer without a trig function in it. Now, it doesn't per se matter. I would be fine with this. But if they don't take it, let's keep in mind that tangent of 4x plus y, what does that equal? Tangent of 4x plus y equaled 4x. So if we think of a triangle, I'm just going to use theta to represent that angle so we don't have to write that whole thing. So if our angle is theta, then from that angle, tangent is opposite over adjacent. So from this angle, that side will be 4x, that side will be 1. The hypotenuse is one side squared, so this side squared would be 16x squared, plus the other side squared, and take the square root of that. What do you mean by that? A squared plus b squared equals the hypotenuse squared. So if we want the hypotenuse, we take the square root of both. So the hypotenuse is the square root of one side squared plus the other side squared. So that's tangent from that particular angle. Notice we have cosine squared from that particular angle. So cosine from that angle, using our triangle, is 1 over the radical, adjacent over hypotenuse. That's cosine. We have cosine squared. So to get cosine squared, we square it. So cosine squared of 4x plus y equals the top squared plus the bottom squared. So the square and the square root will cancel. So dy over dx, if we don't want to leave a trig function in there, we have a 4 out front. Cosine squared is equivalent to 1 over 16x squared plus 1, and that's minus 1. So this is okay. If we got a common denominator, our common denominator would be 16x squared plus 1, so we would end up with that on top and bottom, and then we could simplify that a little bit from there. We've done enough to get to this point, so that would be okay. So if that's our dy dx, then the question also asks, what is the slope at 0, 0? What is the slope at 0, 0? So if we substitute 0, 0 into our function, well, the way we rewrote it, we only have x's in our equation. So we have 1 over 16 times 0 squared plus 1 minus 1. So 4 times 0 squared is 0, so that's 0. 1 over 1 minus 1, which that's 0, so we end up with 0. So if we were to graph this particular implicitly described formula, then at the origin, we would have a horizontal tangent line. Now let's do one more example, and that involves taking a second derivative where we have an implicitly defined function. So how do we get a second derivative? If I have a function and I get the derivative of it, then to get the second derivative, I just differentiate it again. So typically, I differentiate with respect to x again. Y prime, that's also known as dy over dx. And when I differentiate that with respect to x, that gives me what we call the second derivative. That's also referred to as y double prime. But the point here is that the derivative of the first derivative is the second derivative. So we need dy over dx, or first derivative, differentiate with respect to x. This is not x. So the chain rule, general power rule, so bring the 4 down. Y to the 1 less power times the derivative of the inside function. The inside function is y. The derivative of y is dy over dx. On the right side, our variables match, so the derivative of this with respect to x is just 7x to the 6th. Basically here, if our variables match, we just take a simple derivative. If they don't match, we take that derivative and then we pick up dy over dx. But that comes from, this is the derivative of the inside function. So to get dy over dx by itself, just divide. So dy over dx is 7x to the 6th over 4y to the 3rd. So that's dy over dx. Now, this is the first derivative, but we could reduce this. Notice we have a relationship between x's and y's. That it takes y to the fourth power to be the same as x to the seventh power. Those two things being the same, if we wrote the fraction y to the fourth over x to the seventh, anything divided by something that is equivalent to it is 1. And we could also write it the other way, where we put the x's on top, the y's on bottom. That would also be equal to 1. Because we have equal quantities on top and bottom. Just like if I have 3 on top, 3 on bottom, those are equal quantities, so that makes 1. So what is that going to allow us to do? Well, I have x's on top, and I put some x's on bottom. Those will reduce. Well, I can put x's on bottom and y's on top, and that will allow the y's to reduce. That's okay to multiply by, because what are we really multiplying by? We're multiplying by 1. If anything times 1 gives us itself. So this 3 will cancel 3 of those out, leaving us y. This 6 will cancel 6 of those out, leaving just x. So our first derivative can be simplified to 7y over 4x. Did we have to reduce it like that? No, not necessarily. But having smaller exponents does make our answer a little bit simpler. So now that we've simplified the first derivative, now let's take the derivative again to get the second derivative. So on the left side, this is the second derivative of y with respect to x. On the right side, we have a quotient. So we're going to call the top u and the bottom v. So u is 7y. That'll make u prime 7 times the derivative of y dy dx. V is 4x, so v prime would be the derivative of 4x, which is 4. So quotient, the derivative of a quotient is u prime times v minus u times v prime, all of that over v squared. Now, all of that's okay. The derivative of the top times the top times the derivative of the bottom squared. In our answer, we don't want to leave a dy over dx on the inside. We want our second derivative to be in terms of y and x, not dy's and dx. So we can replace dy dx because we know what dy over dx is. It is equal to 7y over 4x. So in place of dy over dx, I'm going to put 7y over 4x. But I'm only putting that where dy over dx is. So dy over dx changed to what we got for dy over dx. So this 4x on bottom, that one will cancel. That gives us 49y. 7 times 4, that's going to be a minus 28y over 4x squared. The top's like terms, so we can subtract that, get 21y over 4x all squared. And we could leave it like that if we wanted to. There are also other ways of writing that using the relationship we had of how y's and x, but that would be sufficient there.